Right. Good morning, folks. Everybody good after the conference party last night? Good. Year is currently 2017. Let's imagine the year is now 2037, and teleportation has finally been invented. Hooray! And I teleport us all to here. Where are you? There. France. Yeah, La Rue du something. Sounds French. Jersey, yeah. So this is where I live. If you wanted to really find out where you were, you could walk down this road, down this leafy lane, and hopefully bump into somebody and ask them, where am I? Or we could use technology to solve this problem. We get out our mobile devices, our smartphones, we open up one of the Maps apps, we hit the little dot that says, find me, and it gives you something like that. Does this help? Does this help you understand where you are? A bit. We've got a nicer overhead view now. It's still quite zoomed in, isn't it? Still not entirely sure where we are. How do we solve this? We do the pinch to zoom out thing. There we go. There's Jersey. That's where I live. It's a small island just off the coast of France. It's quite complex, isn't it? It's quite cluttered, that picture. You can see lots of the textures, the different shades of green. It's not a particularly great way to navigate to an unfamiliar environment. Again, how do we solve this problem with technology? We just remove the satellite imagery. There we go. Now Jersey becomes a bit clearer. We can see the intricate network of roads and lanes, and we can start to see some of the place names. If you don't know where Jersey is, though, again, this is kind of useless. So we have to do the pinch to zoom out. A bit more context. So there's another island next door called Guernsey. This here on the right is France. We zoom out one more time. Oh, there we go. Now we can start to get some better context about where Jersey is. Zoom out one more time. Who's been to Jersey here? A couple of people? Right, so this summer coming, when the weather warms up, because we are still British climate essentially, you should come to Jersey on holiday. When you come through the airport or through one of the harbour, grab one of these things. It's the visitor map. The visitor map is a really good, simple guide to getting around Jersey. Tells you where to go, what the place names are, that sort of thing. It's broken up into 4 quarters, nice simple map. It's mostly accurate. It's a kind of schematic thing. There's a bit of information and detail missing, but this does tell you the major routeways, sites, points of interest. There's a town area. We can zoom in a bit. Again, this is mostly accurate. You'll see that there's a marina here, which is blue. It kind of implies it's covered by water. It is, for 12 hours of the day. If you drive your boat in there and park it, you will come back at some point and find it's laying on its side. So that completely dries out. And also there's a bathing pool at the bottom, just where it says St. Helier. That gets flushed twice a day with the tidal movement we have, which is probably useful because I imagine the kids pee in it in the summer, but whatever. So contrast this map, which is very simple, to this one. This is an Ordnance Survey map of Jersey, and it's much more detailed. It's been created by modeling and surveying, and it's got every single street and every single curve and every single building and every single building shape and the various terrains and the contour lines, and it's just very, very detailed. This is a little bit trickier to understand, but it's got lots of information if you know how to interpret it. The thing both these maps have in common is they show points of interest. So when you come to Jersey, what should I go and see? Well, one of the things you should go and see is this. It's called Elizabeth Castle. It's a small islet off the south coast of the island. Because of the history around Jersey, the French and the British kind of invading, there was lots of fortifications. And this castle was built in the 15 or 1600s, and it's a really beautiful example of like a kind of medieval style castle. Lots of big granite stonework, that sort of thing. When you walk to the center of this castle, there is a kind of natural high point. And you get closer, and you get closer, and you get closer, and then you see something a bit odd. You've got this beautiful granite building, and someone stuck this really ugly concrete thing on top. And you're like, what? Why would you do that? You walk around the castle a bit more. History's important here. So during World War II, This is my short history lesson. During World War II, Jersey was occupied by the German forces. The Germans imported a bunch of concrete and built stuff like that. They also built gun emplacements. So they refortified the existing fortifications. And again, it's only by reading the signs around the castle that you really understand this history, and it allows you to kind of marry these two different styles of architecture together in your mind. How do you find out more information about the history? Where do you buy a travel guidebook before you come to Jersey? Which you should this summer, of course. Physical book, electronic book, tells you lots of really interesting information about Jersey, maps, points of interest, walking routes, sites, itineraries, and so on and so forth. So what has this got to do with anything? Right, I'm not being paid here by the Jersey Tourism Board, by the way, to promote Jersey, although they should do. I'll come back to that stuff later. So Visualise. This talk is really about visualizing, documenting, and exploring software architecture. One of the things I do at the moment is travel around the world, and I help organizations understand software architecture. I run a 1 or 2 day workshop, and a big part of that workshop is it's a software architecture kata. So here are some requirements. Go away, create a solution, draw some pictures to visualize it. The diagrams that are flying past now are real examples from real workshops. There's some really, really crazy stuff going on in some of these diagrams. I have 20 gigabytes of photos like this. Right, we could just spend the next 3 or 4 days just looking at all these diagrams. Sometimes when I'm listening into what the groups are doing, so this is a group exercise, 3 or 4 people. Sometimes somebody in the group will be drawing a thing, like a shape or a line or a symbol, and they will actually say things like this. Right, this thing doesn't make sense that we're drawing, but we'll explain later. Whoops. And there's always this assumption that diagrams will be presented. And there's always this assumption that, there's a narrative needed to accompany the diagrams to really unlock the meaning of the diagrams. And of course, this is fine. If you're working in a nice little group environment and you're having like an hour and a half or 2 hours to design a software solution, you're drawing some pictures, you're having those conversations in front of the whiteboard, those conversations, those diagrams, those icons make sense to you. One of the really nasty tricks I play is I get groups to swap pictures. And guess what happens? You get this gigantic what moment going on because they've now got a bunch of diagrams, they don't know what they mean, they've got funny symbols, funny icons. It's just really, really hard to interpret. So I ask people, well, what's tricky about these diagrams that you have? Give me some review here. And they say, well, we're not sure what these shapes or arrows mean. Why are these lines pink or red? Well, somebody had a pink marker pen, they used it. What is this diagram actually showing? What level of detail is it showing? Why have we got multiple diagrams? Which order do we read the diagrams in? And so on and so on and so on. The actual design part of this exercise is really simple. It's a really, really simple little kind of batch application with a web app, typically. But the complexity in this exercise is just communicating and visualizing and sharing these ideas, the intent behind the design. So I asked teams, what did you find challenging? And they all say the same thing. We don't know where to start with the drawings. We don't know what types of diagrams we should be creating here. What notation should we really be using? What level of detail do we design down to? And what level of detail do we draw pictures down to? These are two very different things, of course. I've run this workshop now a lot. 25 plus countries, 10,000 plus people have done it. I have no empirical evidence to back anything up. Right? This is all purely anecdotal based upon this sort of sample size. But essentially, software architects and software developers really struggle with this stuff. Time and time and time again, everybody struggles with this exercise, it seems. Now, we might be thinking, well, there is this thing called the Unified Modeling Language. Who uses UML here? One? I did ask that question out loud, didn't I? One? Okay. So, well, that worked well, didn't it? And that's, again, what I'm seeing more and more. So UML used to be quite widely used, maybe 10, 12, 15 years ago. Now, hardly anybody's using it. I'm seeing many, many more organizations and teams where nobody on the team understands UML. And typically, and actually I think this is optimistic, it's sort of 1 out of 10 people. I mean, given this audience, this is way, way optimistic, of course. So this raises a rather interesting question. Is UML worth using for describing software, specifically architecture and design ideas? And the answer is, it can be. The problem with UML is it doesn't necessarily have the right type of abstractions that are useful to describe software systems. So let's imagine we want to draw a picture of a user using a software system. You can't do that in UML. UML does not have a software system box. What you end up doing typically is using something like a component or a package shape and adding a little stereotype in brackets to say, this is not a component, as you might think it's a component, it's actually a software system. If you're having to jump through these sorts of hoops, you have to question whether UML is the right notation to use in the first place. And this is why lots of people draw boxes and lines types diagrams. If you've never drawn an architecture diagram before, where do you go for inspiration? Well, Google's a good start. Except it's not. If you go and do a Google search for software architecture diagram, you get that. Page after page after page of very pretty, colorful block pictures, the type of things you can do in PowerPoint, Visio, OmniGraffle, Keynote, Lucidchart, etc., etc., etc. And when I go and see organizations and they let me look at their documentation, I see stuff like this, typically on SharePoint or Confluence pages. And lots of these diagrams don't make sense. Lots of these diagrams suffer from exactly the same problems as the hand-drawn diagrams I kind of whizzed through quickly before. Why is all this important? Good communication. We're all seeking to be leaner and more agile and move fast to respond to business changes and business needs. If you want to do that as a team, you need good communication. That's all this is very simply about. There are two things we want to talk about then, really. Number one is notation, and number two is content. Notation is super simple to solve. Here are some tips. I'm not going to go through these in any detail, but these are the types of things you want to think about if you're drawing ad hoc boxes and lines diagrams to describe your software systems. Be conscious of the notation you're using. Every time you invent an icon or a symbol or a specific line type, ask yourself why, and make sure that's written down with a key or a legend. One of the things we joke about in software is that naming stuff is really hard. Do you think this is true? Yeah, it's true to a degree, isn't it? If naming stuff is hard, it doesn't make any sense whatsoever that most of our architecture diagrams are just boxes with one word in, one name. If the name of the thing is wrong, there's just a degree of ambiguity creeps into these diagrams. So my really simple advice here is just add more text to your pictures. It's as simple as that. Here's an example diagram. The one on the left is what I see people normally do. Lots of boxes, single word. Add more text. Describe what those boxes are. What technologies are these boxes? What are the responsibilities of these boxes? And again, I'll show you some more examples of this later. So notation's easy. Content's much more interesting. Back in the late 90s, Philip Christian, who's one of the RUP guys for National Union for a Process, he created this thing here called the 4+1 view model for software architecture. And it's a way to think about, describe, and communicate software architecture from a number of different angles, essentially. And he says this: to describe a software architecture, we use a model composed of multiple views or perspectives. Anybody using this today? Anybody used it in the past? Yeah, a couple of people. So essentially what this is all about is you take a use case, a scenario, a feature, a user story, and you document it from 4 different angles. You have a logical view that talks about your functional building blocks. We can call them modules or components if we want to. You have a development view, which maps how your functional logical building blocks map onto code. There's a process view that talks about concurrency, and there's a physical view that talks about infrastructure and deployment. There are lots of other ways to do this as well. There are lots of other architecture books, and those architecture books present their own enhancements or extensions or versions of this. And the thing you'll notice about most of them is that they have this weird split between the logical view and the development view. So here's a picture of my software system. It's made up of logical things. And here's a very different picture of what those logical things look like if they're hopefully mapped to code somehow. And this is weird. I don't know why we've chosen to do this in the past. You can see this in some of the older design methodologies like SSADM, There's a logical design step, and then there's a physical design step. And this doesn't make any sense as far as I'm concerned, because the two are intertwined, of course. And I think this leads to this statement a lot. And I see this in organizations around the world. They have these beautiful looking handcrafted architecture diagrams printed on like A0 paper with a plotter. Last updated in 1998 or something. And then they say, yeah, these diagrams are really nice, but they don't quite match the code, by the way. Right, so they're lying to you. What value do these diagrams have? Is there just a big crack that you're covering up? Or do you actively use these diagrams on a daily basis? So again, it's the mismatch between what we think about on the diagrams and what the code looks like. There's a fantastic book, if you're really interested in software architecture, there's a fantastic book by George Fairbanks. It's called Just Enough Software Architecture. In this book, George Fairbanks talks about the model code gap, and it's exactly this thing. So we have a model of our software, a bunch of diagrams, if you will. And that model of our software doesn't quite reflect the code, or vice versa. And explaining this is very, very simple. So when we're having an architecture discussion, we might use abstract concepts to describe the things in our system. We might have a discussion using the terms component and module and layer and service and subsystem. Who's a C#.NET developer here? Right, so that's a good chunk of you. In C#, is there a component keyword? Oh. In C#, is there a layer keyword? Oh. But we often think about our software as being made up of layers and components. And we have these conventions where we say things like, well, a namespace equals a component, or a namespace equals a layer, or maybe an assembly equals a component. And sometimes it's that mapping of, real-world code concepts into the abstract concepts that doesn't make sense, and is often missing. So that's the sort of problem we're trying to solve here. Before we can even attempt to solve this problem, this gap, we have a much, much more pressing issue. And that is, even now in 2017, we don't have a common language to describe architecture. We don't have a common language to describe the things our systems are built from. Now, this is a pretty bold thing to say, I must admit. Because we've been using words like module and component and service and layer for years and years and years, so surely we must understand this stuff. No. Who likes a quick quiz? Do a quick quiz? Excellent. Right, what's that? It's a map of London. Perfect. We're in the right place. What's this blue thing in the middle? It's the Thames. It's a river. What is a river? Wet? Yes. It's a flowing body of water, one way or the other. Perfect. So we learned this stuff when we were kids. We know what a river is, and we know how to go and find other rivers. Let's try something else. What's that? It's a top-down floor plan for a bathroom. What's this thing here? It's a toilet. Excellent. What is a toilet? Seriously? There's an exercise here for later. Right, so it's another body of flowing water, ideally one way. Again, we learned this as a kid. We know how to identify, depending on country, other toilets. And we can go and identify more toilets if we want to. Perfect. Any electrical people here? Excellent. So what's this sort of squiggly thing down here, this zigzaggy thing? A resistor. What is a resistor? Resists something or other, yeah. Slows down the flow of current or something. I'm not an electrical person. If I had a box of electrical components here on this table with resistors and capacitors and switches and LEDs and all sorts of stuff, could you come to the front, rummage through the box, and find me a resistor? Yeah. And if you knew the color coding, you could work out how strong that resistor was. So again, we know what a resistor is. We can identify it. We can pick it up, touch it, feel it. See, this quiz is far too simple. Right, let's go exponential. What's that? See, everyone's sat for that. What? Okay, let's backtrack. What type of diagrams are these? Class diagrams, close but not quite. Component, right, so these are UML component diagrams in various different formats. Given that these are UML component diagrams, what are each of the boxes on the diagrams? Components, thank you. Yeah, so each of these boxes is a component. That's what this UML shape or notation means. What's a component? Something that does something. I ran my workshop late last year, and somebody said, it's an imaginary thing. Right, so you build software systems out of imaginary things. It's a logical unit of function, yeah? That kind of works as an explanation. Let's look a bit closer at these diagrams. So that one there is stereotyped database. So that is a database component, because there's a little stick with a lollipop saying JDBC. That sounds like there is a Java interface into that database. So that sounds like a database, right? Like MySQL instance or something. So that's a component. On the left-hand side, we've got some components that are labeled UI or application. I don't know whether these are web applications, console applications, mobile applications. I don't know if these are separately deployable things. The slice through the middle. You remember what I said about naming and adding more text? I have no idea what these components are or what they do. Seminar, schedule, brilliant. I don't know whether these components are microservices, right? They're standalone deployable things with a remotable interface, or they could be part of the application. There's just so much ambiguity on this diagram. The other one is absolutely brilliant. So this is a real example from a modeling tool. I won't tell you which one. There's a firewall component, I guess. There's an XSL style sheets component. What? What else have we got? There's a web server component, an ASP pages component. I don't think I'd ever draw an architecture diagram like that. My favorite, of course, is the business logic component. That's epic. To boil this down to its absolute essence, right? Imagine we're building a software system. The software system is built from a web application that talks to a database. If you go and look up the word component in the dictionary, it means part of something bigger. For some people in the room, the web application is a part of the system. It's a component of the system. For other people in the room, that logging component is a component. Both make sense, but they're just very different levels of abstraction. It's the irony of the ubiquitous language. We talk about domain-driven design and creating this ubiquitous language between us as techies and the business people. We don't have our own ubiquitous language. That's exactly what this is about. If you look at the Unified Modeling Language, UML, it tried to do two things. It tried to create a ubiquitous language and a ubiquitous notation to describe the language. I think having the common set of abstractions, I think creating the vocabulary is actually much, much more important than the standardized boxes and lines. If you look at something like electrical engineering, if I draw a little squiggly thing, we know it's a resistor. I really would like us as an industry to get to that point, but I don't think we're there yet. And I think we need to focus on the abstractions first and let the notations evolve naturally. This might sound a bit foolish. If we go get two tourist maps of London and lay them out side by side, the two tourist maps of London will show the same things, won't they? The various areas and districts and the Thames and the tube lines and the bus routes and the shopping centres and that sort of thing. So the two maps of London will show the same things, the same abstractions, but they might use a different notation. Different shadings, colours, line styles, icons, symbols. How do we decipher the maps? Well, there's a key in the corner. Perfect, let's do that. So a map is a really nice simple example of a common set of abstractions with a self-describing notation. And that's a really, really powerful concept. So, how do I think about software systems? For me, a software system is made up of a number of containers. A container is something like an application or a data store. It's a web app, a mobile app, a console app, a Windows service, a database, a file system, an Amazon S3 bucket, something running in Azure, whatever. It's something that needs to be running for your system to work. For me, my containers are made up of components, so I want to use the word component to mean something running in a runtime environment, essentially. Yeah, it's a grouping of related stuff with a nice, clean, simple interface. And because I mostly deal with Java and C#, my components are built from classes, ultimately. And we're done. So this is a really, really simple hierarchical structure to describe the static structure of a software system. Software systems, containers, components, classes. If you're using F#, not really classes, are there? So maybe in F#, it's not components and classes, maybe it's modules and functions. Haskell, same thing. JavaScript, modules and functions, modules and objects. So you might have to take this hierarchical approach and kind of map it to the tech that you're using. This is my language, this is my set of abstractions. We can then draw some pictures to visualize this stuff, and this is what I call the C4 model. I have a system context diagram, shows my system and stuff around it. We zoom into the system boundary to show containers. We zoom into each container to show components, and then we probably stop. What I normally find is going down to the level of components is normally sufficient to describe my software. If you want more detail on specific components, yeah, you can zoom in if you want to. If anyone's done some work around big data, you might have heard of Schneiderman's mantra. If you have a huge amount of stuff to work with, you want an overview of something first. You then want to zoom in and filter to specific parts of that set, and then you want some details on demand, and it's the same sort of thing. Just as a really quick, silly example, when I moved back to Jersey, 2008, I built this thing here, techtribes.je. It's a really super simple content aggregator for the local tech industry. I've now since taken it down. Lists local people, businesses, blog posts, tweets, that sort of thing. This is a system context diagram for the TechTribe system. That box in the middle, that's my system, and these are the things around it, different people, users, actors, roles, personas, and different system dependencies. If this was interactive, like a Google map, we select the TechTribes box, we pinch to zoom in, we get to see the containers inside it. So this dashed line here represents the system boundary, and all of the boxes inside the system boundary are the containers that make up the TechTribe system. There's a web app, a standalone app, and some data stores. You'll notice my diagrams have lines, descriptions, technologies, the arrows are annotated, so on and so forth. Again, if we're interested in some more detail, we select one of the containers, we pinch to zoom in, we get to see components. So this is the component diagram for one of those containers. And the story repeats until we get down to a class diagram. So a nice, simple set of hierarchical diagrams that actually reflect the structure of the thing we're building. And it's all about maps. It's the same thing as I presented at the start. We have different levels of maps for different audiences, depending on the different types of stories that we want to tell. And we do want a way to zoom in from one level to the next, and there to be some real traceability here, of course. This is just about static structure. I am trying to tackle this static structure first, so we have the code up to the system with a couple of levels in between. Once you understand that static structure, the other views that you might want to use to describe your software are super simple. If you have a feature or a user story or a use case that you want to show how it works at runtime, you draw a UML sequence or collaboration diagram showing how elements in the static model interact at runtime, whether they are classes, components, or containers, up to you. If you have a map of your infrastructure, routers, firewalls, servers, that sort of thing, whether it's virtualized or physical, there's a mapping between containers and infrastructure. That's your deployment mapping. Again, super simple to do. So this is what I teach on my course. People tend to love it. Somebody this week asked me if I was going to submit it to a standards body, which sort of scared me. I'm not sure how I answer that question. And I force people to do this on paper. And it really bugs them, because there's me saying, add more text to your diagrams, and now they're going nuts, writing all this little tiny text on pieces of paper. So after this, at some point, I always get this question, well, what tooling do we recommend? And whenever I poll a team, I say, well, what tooling do you use currently? And they say, we use Visio, or OmniGraffle, or Glyphy, or Draw.io, because we use it in the cloud now, or Lucidchart, or Diagramly. There are lots and lots of these kind of general-purpose diagramming tools out there. And I'm sure you've used them in the past as well. And because the diagrams I've shown you are just boxes and lines, you can draw them in general-purpose tooling. You create a box, you put some text in it, you make the text the right size, the right color, you line it up, you draw another box with the same thing, You draw a line between the two boxes. You open up the properties for the line. You try and figure out which is the start and end of the line to put the right arrowhead on the right side. You always get it wrong first time round, trust me. And you kind of rinse and repeat. And it's a very manual, laborious process. The other thing, of course, with something like Visio or a static diagramming tool is that if you have the same box on two diagrams, if you change it on one diagram, it doesn't magically change on the second one. So if I rename a person, a user, a component, I have to go and rename that thing on other diagrams. With great power comes great responsibility. Come on, it's 2017. Do building people do this? You know, you've been tasked with architecting the Burj Khalifa. Did you get Visio out? I hope not. The building industry uses, sophisticated, complex modeling tools. We create a nice three-dimensional model of the thing we're building, and we surface different diagrams, different views from it, cross-sections and side elevations and so on. The irony of this, of course, is that we build these tools for other people to do modeling, but we can't do modeling ourselves. How funny is that? Once you have code, why don't we just reverse engineer diagrams from code? Has anybody tried this? What happens? You get an awful mess. Is that because your code is an awful mess? Sometimes. But more often than not, these diagramming tools are just showing you everything at a very, very low level of detail, of course. Apologies for the Java nature of this example, but everything I'm going to tell you is exactly applicable to C#. So in the Java world, there's a framework called Spring. Spring does everything. That's all we need to know. Part of Spring is an MVC framework for building a model view controller web apps like ASP.NET MVC. This diagram on the left is an architecture diagram for a sample application called the Spring Pet Clinic. So this is a toy application, a toy code base to illustrate how to build Spring MVC applications. Basically, it's a three-layer architecture: controllers, services, repositories. You download the code off GitHub. It looks like this. You load it into your IDE. You say, IDE, generate me a class diagram of all of this lovely code, and you get that. And this is a small sample toy application with like 20 or 30 things. This is not your enterprise systems with millions of lines of code. I promise you, I did try to move these boxes around so that there were no overlapping lines. It's basically impossible. It's too much detail. If we take a more thoughtful, balanced view, maybe we exclude some stuff that's not really important to having an architecture discussion. And again, this varies code base to code base, but in this example, if I start to remove some of the really boring things, like my utility classes and my data structures that don't have any business logic in, I can generate a much, much simpler diagram by removing stuff from that diagram. And once you start to rearrange the boxes, I can now redraw that layer diagram again. So the boxes at the top, the classes at the top of my web app controllers. There's a bunch of service stuff in the middle. That's my business logic layer, my service layer. And all of the things down here are my repositories, my data access objects. But this is still fundamentally showing code, isn't it? It's still showing me classes, interfaces, links between these things. If this was a Google map, this might be like Street View. So let's imagine I live in Jersey, I've never been to London. I fly to London for the first time. I manage to get on a train to London somehow. I walk out of London Victoria Station, and I'm lost. Aha, but I have my smartphone with me. So I open up my smartphone, and I do the Find Me Now thing, and then I switch to Street View. So I'm standing outside the train station. I have the Street View in real life and Google Street View here. Well, that's a dumb idea, isn't it? It's like the same thing. I'm just wasting my roaming data. What I really want to do is zoom out of Street View to get a more high-level overhead view. And that's the thing. How do I zoom out from this picture? Well, I have to make some assumptions. If this is showing me code and classes, and I want to see components, I have to work out what a component means for me in this code base. And this is my approach for this code base. So I'm going to treat all of the web app controllers as separate components because they're separate things. And I'm going to bundle up the interface and the implementation class for everything else. Down at the bottom, there's also some little tangle of helper classes, so we may or may not want to include those in our component definition. So of course, the diagramming tools, when you reverse engineer the diagrams from code, They see codes, they don't see components. And this is not a new problem, of course. This is just the model code gap thing again. We go back in time. There's a great paper if you want to read it. The first two opening paragraphs basically illustrate the whole thing. You ask a developer to draw you a diagram of the system they're working on, you get a nice high-level picture. You reverse engineer something from the code, you get a totally different picture. The low-level picture, auto-generated, is super accurate, super precise, but it doesn't necessarily match the way that me as a developer, how I think of the code base. And one of the big problems here is that the architectural information doesn't live in the code. It gets lost at some point. George Fairbanks to the rescue. Right? So in George Fairbanks' book, he talks about adopting an architectural-level encoding style. This sounds very grand. It's nothing more than dropping hints and metadata into your code base so that your code base does reflect your architectural ideas and intent. In very real terms, this is stuff like adopting a naming convention consciously. So if I have a diagram here and there is a box that says logging component, let's make sure something in the code is named logging component, so there's nice one-to-one mapping. Maybe it's a namespacing or packaging convention. Maybe we say that every box on this component diagram maps to an assembly or a namespace. Maybe it's about adding machine-readable metadata like attributes or annotations to say, this is architecturally important. This is a component, for example. I also want to get people away from using Visio. Not because Visio is horrible, but, well, it is, but it's not the right tool to draw architecture pictures. Now, there's something called an architecture description language. Has anybody used one of these things before? No. I thought that might be the case. These things are essentially textual descriptions of architecture, normally static structure. So you write some text, and that text describes your software system to some degree. There are a bunch of these things out there. Darwin, Koala, there's one called Acme, believe it or not. And they never really left research and academia. If you do a search for Darwin, architecture description language online, you end up on a university website. There's a PDF file you can download with the language grammar. It's horrible. You do not want to go to a conference talk that teaches you these languages. No. However, as developers, we like text, don't we? We can diff text. We have lots of tooling to support and refactor text. We can check text in. Text is good for a number of reasons. So why don't we take all of these ideas and throw them into a big pot and see what comes out? So what I've done is I've created an executable architecture description language. And there are two open source projects on GitHub, Structurizer for Java and Structurizer for .NET. And essentially what these things are is they are small class libraries that implement the C4 model. I'm going to show you some Java code. The C# version is almost exactly the same, except you have to uppercase the first letter of the method names. That's it. What we're doing is we're really creating a model of our systems. Let's create a model that describes the Spring Pet Clinic system. The Spring Pet Clinic system is nothing more than me as an employee of the clinic using the system. That's it. There's no more complexity here. So basically, I can create that description using code. So I'm going to create myself a software system object and give it some properties to represent the Spring Pet Clinic system. And I'm going to create myself a person object to represent the user. And I'm going to say, using the API, that the employee uses the system. Done, that's it. So it's a really nice, simple, kind of domain-specific language to describe architecture. You're just building up an in-memory object graph. From a container perspective, this is nothing more than our web app talking to our database. Again, we can model up with code. Create a container object for the web app, create a container object for the database, wire the two things together in various ways. When it gets down to the level of components, I don't want to have to do that. Why? Because it's long-winded and it's error-prone. Every time you add a new feature, you might change the list of components in your system. So built into both libraries, there's a component finder. Guess what the component finder does? It finds components. See, naming is not hard after all. You plug in different strategies because every code base is different. Every code base has a different approach to how it thinks about components. So that part, you can plug in your own strategies. Naming conventions, so go and find me all of the things that end in the words component or service or controller, for example. In this case, there's a pre-built Spring component finder strategy. It knows how Spring applications work. All it essentially does is it looks for special Java annotations. And then using some bundling logic, it basically joins together the interface and the implementation class. And it also finds some supporting helper classes. So you run the component scan. You run this against the compiled version of the code. So you run it against your assembly in the .NET version. It uses static analysis and reflection to go find stuff. Once you have a set of components and the relationships between them, it finds those as well. You can write some more code to say things like, go and find me all of the data access objects or data access components you just found and make them use a database. So again, you've got complete control over all this stuff. So that creates you a static model of your software. We then create some views. There are a bunch of view classes in the library. The view classes map onto the C4 diagrams. We create a context view, a container view, a component view, and you get control over what you can add and remove from the pictures. And then we need some pictures. Right, so this is just a little standalone program. We need some pictures. We need to visualize this. And of course, what we have here is a model. And once we have a model, we can visualize it in a million different ways. Anybody like GraphViz here? No. So in the Java library, there's a GraphViz exporter. So you take one of the views, you export it to the GraphViz format, you throw it into GraphViz, and you get an automatically generated diagram. Any UML fans here? One, I know. So if you've heard of Plant UML is a textual way to create UML diagrams. Again, there's an exporter for Plant UML, and it generates you a bunch of pictures. So these are UML diagrams to describe the Spring Pet Clinic system. Context diagram, container diagram, components. So all of these components were found by the component scan plus all the links between them. I want pretty diagrams for presentations, and pretty diagrams are just nicer. So I built some tooling called Structurizer. Structurizer is a software as a service thing. I have to be a bit careful here. I'm not trying to sell Structurizer. There is a commercial aspect to this if you want to do lots of kind of company sharing stuff, but there's also a free version that you can create diagrams with. With the free version, what you do is you upload your model as a JSON document to the web API, and it draws some pictures for you. So there's no automatic layout, but this is the context diagram for the Spring Pet Clinic system. It's the user using the system. This is the container diagram. It's the user using the web app using the database, and that's the component diagram. So again, a slightly nicer approach to visualization here. Again, because this is a model, we can generate things like diagram keys automatically. Hooray. So now we can focus less on notation. And again, it's the diagrams and maps thing. What you can actually do with structurized diagrams is you can double-click on a box, and it goes to the next level of detail down. If anyone's seen the Contoso University sample, ASP.NET sample, again, same sort of thing. So there's an example, user system, user web app database, and these are the components in the Contoso University sample. Those are the structurized diagrams. Somebody sent me an email a couple of weeks ago saying that they'd used the open source structurizer for C# library and done an export to DGML. DGML is natively supported by Visual Studio, and you get some diagrams that look like this. He's working to make the diagrams look nicer, but you get complete, hierarchical, expandable diagrams inside Visual Studio, which is quite cool. I don't know whether he's going to make this open source or commercial, but definitely keep an eye out for that stuff. If you hook all of this stuff up with your build process, guess what happens? You get diagrams that reflect the code and diagrams that are kept up to date. And that's exactly the point here. We shouldn't have to worry about recreating diagrams every time we make some major changes to our software. So that's visualization in a nutshell. There are two other parts of this talk. We'll just come to very, very shortly. Documentation. This is what the Agile Manifesto says about documentation. These 5 words have been misinterpreted massively over the past 15 years, and lots of teams don't write any documents anymore. I'm sure you don't do that, do you? Don't comment. The problem is, of course, the code doesn't tell you everything. The code can't tell you why decisions were made. They can't tell you, what the approach is to security on a holistic point of view. Where do we deploy this thing? How do we maintain it and support it? Where do errors go? That's hard to find just by scraping information from the code. A lot of teams still take this approach. They create some sort of like software architecture documents. There are millions of templates out there. And they describe some really useful information very, very badly. Typically these documents are hundreds and hundreds of pages, and half the stuff is totally out of date. That's why these are called SADs, because that's exactly how it makes you feel when you have to write these things. How do I approach documentation? Naming. I like the content in these software architecture documents. I don't particularly like the implementation approach in many cases. So what I do is I rename this to be a guidebook, a software guidebook. And it's the same thing we saw at the start of this talk. So when you come to Jersey, you get a guidebook. It gives you a nice, simple overview. Some nice maps to navigate the unfamiliar environment. That's what the diagrams do, of course. The sites, the points of interest, the itinerary. So, given this island, what's important? What should I really go and see? Apply that to your software systems. Given my million lines of code, which bit should I really talk about? How do we support it, deploy it, maintain it? So some of the practical information, and also history and culture. Right, given this software system, this code base that's been living for 10 or 20 years, why has it evolved in the way it has? Let's write some of this stuff down. And essentially, in my documentation, I'm describing what I can't get from the code. That's it. That's my simplest possible tip I can give you about documentation here. This is a constantly evolving thing. This is not big design up front where we create a 100-page document and then we get it baselined and signed off and there are no more changes to it. This is something we write in complement to the code. And the scope of this guidebook is a single software system, a single product, a single thing. Again, people say, what tooling do we use? I don't care. Well, if you want to use Word, go for it. If you want to use SharePoint, good luck. If you want to use Confluence, a lot of the teams I work with, they use Confluence. Some of the teams now are using things like Markdown and ASCII-Doc. They're creating one file per section of the guidebook. And then they have an automated build process, takes the ASCII-Doc, takes the Markdown, does some stuff with it, generates HTML, uploads it to a website, some description. So again, there are lots of options for creating documentation here. How long should documentation be? Right, forget about numbers of pages. That's the wrong measure. Imagine I join your team. I have no idea what your software does. What I want is something I can read with a couple of coffees over a couple of hours to give me a good starting point for exploring the code. You fly over to Jersey on the 35-minute flight. You read the guidebook on the way. You get to Jersey. You don't know exactly where everything is, but you know what you want to go and see next. So again, it's that starting point for exploration. And finally, exploring. Right, sometimes it's really useful to explore your code base, to explore your software architecture model. And that's the thing. Once you have a model of your code, at different levels of abstraction, you can explore it in really different ways. This is a JavaScript D3 visualization of the static structure for the Spring Pet Clinic system. So this is a visualization, again, provided for free at Structurizer. But JavaScript D3 is very, very simple. And so you can create your own visualizations very, very simply. So we have the Spring Pet Clinic software system, the containers, the components, the classes, the code. So 4 different levels of abstraction here. If we zoom in a bit, this is showing you all of the code level elements for this particular component. The different styling I've applied allows you to see different things about these classes or interfaces. So this owner repository thing in bold, that's the interface type I've identified for the component during the component scan. The not bold, but regular font, there are 2 of them there. These are code elements, classes in this case, that are only part of this component. And the gray code level elements are actually shared between this and other components. So again, you can apply some additional levels of exploration on top of a really simple model. If you have a map of your components and their dependencies, you can draw things like dependency maps. So these are all of the components in the Spring Pet Clinic web app. What I've done is I've selected the clinic service, and the different color lines are showing me ingoing and outgoing dependencies. If there are some cyclic dependencies, we can highlight those things in red. If you have some notion of size or complexity, again, you can do something like a bubble graph. So this is showing you all of the components in the Spring Pet Clinic web app ranked upon size, where size is basically numbers of lines of code that make up that component. You double-click to zoom in, you can see all of the code level elements, and again, how big they are. If you want to do more around exploring code bases, something I would recommend is going to have a look at a product called Code Scene. If anyone's familiar with Adam Thornhill and his Code as a Crime Scene book, him and his company, they've built some tooling to explore a code base. In addition to lots of similar kind of static analysis, it actually does some human analysis on top. So you point it at your source code system, and it starts to show you, how do these people map onto this code base? And you can ask questions like, are we following Conway's law or breaking it, and so on and so forth. So it's some really interesting stuff in there. Right, quick summary. So, look, 2009. So there's an article on infoq.com from 2009, and it was a virtual discussion panel on the future of software architecture documentation. There are some big names here: Grady Booch, Len Bass, Owen Woods, and I've highlighted some really interesting things here. Yeah, we want to see the architecture in the code. We want to embed information. We want to get information free with a click of a button. I don't think we're there yet, but hopefully some of the techniques and ideas and tooling I showed you helps us get a bit more towards that vision. I have two things to finish off with. Number one, the 1990s is calling and it wants its tooling back. Please, 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 please stop using Visio, or Glyphy, or Lucidchart, or Draw.io, or any of those general purpose diagramming tools for describing software. And more importantly, whatever tooling you use, whether it's whiteboards or pieces of paper, within your team boundaries, focus on the abstractions first, so make sure you know how you're going to describe your systems, and then let the notation evolve. That's the simplest advice I could give you there. So make sure you do have that ubiquitous language in your team boundaries. If you want more information on any of this stuff I've spoken about, you can grab my books off LeanPub. You can actually read these for free online. And all of the stuff we talked about is in this book here, number 2. That's me done. Thank you very much. Any questions? Yes?
How much, if any, architecture and diagrams do you should do up front at the beginning of the project before you've got code base?
Oh, that's a good question. So the question is, how much design and architecture and diagrams should you do up front before you start writing code? For me, the short answer is I'm trying to do just enough. Right, and that sounds a bit kind of blasé, but for me, just enough is basically doing enough thinking to understand the structure of what you're building. So in real concrete terms, for me, this means designing down to the level of components and stopping. So once you design down to the level of components, which you can do very, very quickly, you get a really good view of how your responsibilities are carved up across your system. So down to component level design, unless you're doing microservices, you stop one level up. You need to draw some diagrams like the diagrams I showed you. So that's a really great way to share that vision and those architectural ideas with other people on your team. And it's also about risks. So you look at your design and say, right, where are our major risks? You do a kind of risk identification exercise, and then you might spike out some of those risky parts. So that's my typical approach to doing upfront design. And drawing the diagrams, doing the design, even for big systems, you can do in a few days or a week. You add a bit of prototyping, proof of concept. So, for me, I'd have an upfront design phase of a small number of weeks. Excellent question. Yes?
What do you feel is stopping this from getting more traction? Because I guess you're now still being taught at universities.
So the question is, what's stopping this from gaining more traction? It actually is gaining more traction. So you should see my calendar. It's just nuts. The universities are starting to realize that UML is not being used in industry. Some of the better universities I've done some work with, their university lecturers are actually part-time software developers and part-time lecturers. And what I see in those kind of more practical approaches to university courses is that they're now teaching things like my C4 model in universities, because they realize when these people get out into industry, the whole UML thing is just wasted. So we're getting there slowly. There are other architectural formats, SysML, Archimate, but again, the usage of those is very, very thin on the ground. Any questions over here? Yes.
So, as I understand it, you recommend you use Structurize?
Structurizer. So I mean, that's how I do this.
So that's a software you can use that will allow you to, when you change one box, it will reflect more.
Yeah, so the purpose of creating any tooling is to go back to creating real models of a software system. So the problem you got with static diagrams is that you make a change here, you have to make that change in a bunch of other places. If you go back to tools like Rational Rows, Rational Software Architect, Spark's Enterprise Architect, although those tools are big and complex and they tend to favor Archimate and UML as notations, the concept is still the same. They're trying to give you a way to create a model of your software system. You drag the model elements onto diagram canvases, you rename the thing in the model, and the diagrams magically update. So, tooling aside, what I would urge people to do is to think about creating a model of their software system, and ideally trying to get that model created as automatically from the code base as possible. Anything else? Over there, yeah. So, to create some diagrams. Yeah. So the question is, if you have an existing code base, how do you go about creating some diagrams from it? And what I would tend to do is I would tend to try and look at the code base and see, right, how can I identify components from this code base? So yeah, start at the bottom, start the classes, start understanding how you think about the code base. What do you consider to be a component? Are you using a layered architecture, a ports and adapters architecture? How do you carve out component boundaries around sets of classes? In some code bases, that's really easy to do because it's been designed and built in a nice, well-structured way. If you have more of a horrible, legacy, messy code base, that's a bit tricky to do. And sometimes you just have to say, sorry, we can't diagram this system because it's just really a mess. And sometimes that gives you the incentive you need to go and start doing some refactoring. So on existing code bases, I'll definitely grant you it can be tricky. Excellent. Thank you very much again.